All right, let's continue our journey. So now I presented to you a few of the components. There are more, but the idea is that it's a Lego game. You can combine any expression with any other expression. The worst thing that happens is that it doesn't make sense, and then you get an error or something that is weird. But basically, you can put any expression inside any other expression. Here's an example. Where you have some complex expression with plenty of expressions inside expressions. Let's see what it does. 2 plus 2, that gives you 4. Then you have this big object .b, so that extracts the array. Then you have the unboxing of the array, pops it open. Then you have .a that extracts 4. Then 1 to 4 gives you 5. 5 to 50 gives you this. Who agrees? Who doesn't agree? You can just look at it offline, right? Just take this and you just, like your mathematical formula that you compute step by step, tac, 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 tac. Okay? And that works with any expression inside any other expression. Now, just a word of warning, you know that in mathematics, you learn that multiplication has precedence over addition, right? Do you remember these rules? If I tell you 2 plus 3 times 4, that's 14. Right? Because the 3 times 4 has to be done before the 2 plus. It's the same here. In fact, when you have a functional language, you also need to design a few precedent rules that tells you what has priority order what. Now, I don't know for you, but I'm a human being and my brain is a bit limited. So I don't know that whole list by heart like we would know for multiplication in addition. But you know what to do, right? Just use parentheses. Right? If you want to override precedence, you can use parentheses. But also, if you don't know, then use parentheses. Right? Then you're sure that you get the precedence in order. Right? Just for reference, I put the actual order in here, mostly with the highest precedence is at the bottom and the lowest one at the top. But again, just put parentheses. Put parentheses, you're safe. You know exactly what is executed in what order. Okay. Now, one of the benefits of the Lego game is that you can make JSON dynamic. It means that you can build something that looks like JSON, except that inside you nest a query. For example, you can have here an object where you build some things dynamically. For example, as the value for at, it's the string length of foobar, that's going to be a 6. And then inside the array, you can nest a 4 return expression. It's called flower. I'll come back to that. For every I in 1 to 10, return as a long. So here it's an array of long integers, 64 bits, and that's it. And you have that object. So you see how it's a better JSON. It's a dynamic JSON where you just write down something that looks like JSON and then you replace the parts that you want to compute. For whom does that make sense? Right. By the way, everything I'm showing you, you can put it in the Jupyter notebook, in the Docker, it just works. Right? Okay, now let's throw in a few more of the Lego components. There's the if then else expression. The if then else expression evaluates the condition. If the condition is true, then it's returning whatever is in the then, and if it's false, it's returning whatever is in the else, right? It's a functional if then else, right? If you would look for the equivalent in C++, that would be the ternary operator with question mark and colon. Who's already seen that? Okay, then forget what I said. That's just a functional version of the if then else, and it just returns either the then part or the else part, depending on the condition on the top. Okay. Then you have a switch case return. By the way, you don't have to use the switch case return. You can always do it with a cascade of if then else, right? But some people like the convenience of the switch case return. You basically look at some value, and then you look at all possible cases. Is it CH, is it F, is it div, is it I? And then you return, in that case, the languages that are spoken in there, right? So this is a switch case return. Again, it's a functional version of that. It just returns a sequence of items depending on what a value matches. Then you have a try-catch. Who has already seen a try-catch? In some languages like Java, Python, it's basically to recover from an issue. Imagine that you divide by 0 or something like that. Then you can make sure that it doesn't crash the whole thing with an error, but you recover from it. For example, imagine that you have country code, and then somewhere in your data set, it turns out that it's not an integer, and you try to cast it to an integer. Well, instead of throwing an error, you instead return a string, right? So that's what it does. Okay. Now let's get back here. What can we do? So imagine that I have my data set, Git archive, the one at the exam. I have .payload.commits. So that's going to return arrays, because if you look inside the object, there's an object with a key payload that has a key commits, and that's an array of objects. So if I do .payload.commit, I get a sequence of arrays of objects, right? And then if I add this unbox operator, it's opening the arrays and it's flattening everything again, because the sequence of items is always flat. So you see how I can navigate, right? Now that I'm at that level, I open the arrays and get everything that was in the arrays, all of the objects that are in the array. So these are all my commits in any GitHub event. And then I can continue with .author.email, and you see how I end up with all email addresses in the repository, right? I'm not saying you should do it, data protection and so on, but that's an example, right? Everything that I teach you has to be done with responsibility, right? I'm teaching you the technology. Size of an array, that's the size function. So imagine that now I go through the file with the git archive.json. I filter. What is my filtering predicate? I want the size of the commit array inside payload. I want the size to be at least 5, 6, 7, and so on. So anything that has at least 5. Look at this, right? The first one wouldn't work because there's only 3. The second one doesn't work. The third one doesn't work. The fourth array works. Here there's exactly 5. So the fourth array would make it through, right? And basically, I'm returning all of these objects such that the array is more than 5, and then I'm counting. So what that tells me is that in my GitHub data set, there are 5,643 events, such that if I look inside that event, the array located at payload commits has at least 5 elements. Who is with me? Okay. So that's just an example of combining a query. I can also test for an array at an element at a specific position of an array, right? If I want to look at the first committer, if I have all the commits, I want to look at the first commit, then I use a pair of square brackets. Why? If it's just 1, it works on a sequence. If it's 2, it works on an array. That's the difference. So here, for every one of these arrays, I'm taking the first item in there, then the author, and then the email, and I get 34,000 of them, right? Then here's another one. Now I use a cascade of lets that was also in the tutorials that I gave you. It's just a more step-by-step way of writing a query. So I'm looking at the path, then I open the file that gives me the events, then I look at the actors. There's plenty of them, right? Then I look at the logins by navigating inside login. Then I look at the distinct logins by calling distinct value on logins. So you see every variable depends on the preceding variables, right? So when you write a query, you can either do it like this by nesting expressions in expressions, or if you want to make it easier to read, just do it as a cascade of lets. The two styles are totally okay. If you have a larger query, then maybe using lets is going to make it easier to read by a human being. Right? Okay, who understands that query? Right, I just built on top of the past. Who understands? A few raise hands. Okay, look at the tutorial again. I have a whole tutorial that explains that. Lets are really convenient, and almost any functional language that has that. Like if you look at Haskell, Camel, F#, and so on, they almost always have lets in the syntax. It's just a way to explain your thinking in terms of step by step. Okay, now lets are one thing. There's also fors. For is an iteration. It means that for every one of these events in the JSON file, I'm going to bind the $events to one at a time, one after the other. And for each one of them, NB commits will be the size of the array. And for each one of them, I'm returning the event ID inside the ID field, and I'm returning the number of commits set to the number of commits, right? So that's the list of my events, but I only have the ID and I have the size of the array in payload commits. Who understands that? Right? Okay, that's what it does. You see how now I use a for, I use a let. I use an object dynamically because I put the keys in there and then I dynamically populate the values, right? And you see the magic, how it outputs right back at you a collection of objects. So since we've looked at this for and this let's look at flower because this is how it's called. F is for L is for let, W is for where, O is for order by, and R is for return, right? It's called the flower expression. It's on purpose, not the same order as the actual flower in English. That was how it was called back then. I suspect that it may have to do with the fact that one of the very early inventors, her name is Dana Florescu, so it might be as an acknowledgement to her work. So here we have an example with a let clause. So let $x equals 2, return $x times $x. So 2 times 2 is 4, right? Then we have here an example of a for that iterates through the integers from 1 to 10. So again, 1 to 10 gives you a sequence of 10 integers. Then the for is going to one by one bind $x. And for every one of these bindings of $x, you contribute one object when number is $x and the square is $x times $x. For whom does that query make sense? And the results too? Okay. All right. Now, what does the where do? Well, the where acts as a filter. It means that here we iterate on all the values between 1 and 10, but not all of them. The where is going to be picky about them. It's going to say, yes, you iterate over them, but only keep those bindings for which $x minus 2 is strictly greater than 5. Right. I could also, by the way, I could actually update the size. I could also have put the greater than sign in there. I started to remove the GT, EQ, and so on because most of the time it's optimized. And so you actually don't have to use explicitly GT, GE, LE, LT, EQ, and NE, right? So it's totally fine to just put greater than as the sign too. But anyway, where $x minus 2 is greater than 5, so it means it's 7 is not going to work, 8, 9, and 10 are going to work, right? 8, 9, and 10 pass the filter. Who agrees? Okay, so 8, 9, and 10. So here you have the squares, $x times $x of 8, 9, and 10. So you see that's what the where clause do. It just throws away whatever doesn't pass the predicate. So the way to look at these flower expressions is top-down. You start at the top and you go clause by clause, and you just go through the flow of the bindings. Here's another clause, order by. If you know SQL, that shouldn't surprise you. Here we go over the collection. Every object is bound once to $x. And then the order by is reorganizing the order of the bindings. Now we sort by population descending, and then we return the name, right? So we have India, China, United States, Indonesia, and so on, right? Who understands that query? Okay. That's just like SQL, in fact. Maybe it starts looking like SQL because that would be in SQL. Select name from countries, order by population desk, right? You see, it would be the same in SQL. Okay, now you have group by. Group by is also like SQL, but it's more powerful than SQL because this you couldn't do with SQL. So imagine that I create an object with all my continents. Then inside that array, I'm going to compute the continents. How do I do that? I iterate over the countries, and I have this group by. It means that I'm putting the countries in little packets. Every packet corresponds to a continent. So I say group by continent equals x.continent. That creates my packets. What happens is that after the group by, I'm going to have packet by packet, but now $x is going to be bound to the sequence of the objects in the same packet. Before the group by, it's one by one. After the group by, X has the packets. So it means that for each packet, I create an object. Continent will be the name of the continent. That's my grouping key. There's only one, right? That's the string. And you see in countries, $x is the sequence of all the objects from the current continent. .name will list them, right? North America, United States, Canada, and so on. Who understands that query? Right? That's the group by. You cannot do it in SQL. Because in SQL, the group by will only work with atomic values. Everything that's not the key, you have to count, sum, average, and so on. But you see what happened here? We do not compute a sum over the name or an average or anything. We just list them, right? That's the magic of a language that works with denormalized data, because you can actually do this, and you can output something that's not actually a table. It's nested data. You have an array in an object, in an array in an object, right? And that works with a query like this, where you just nest expressions into expressions. Okay, so now who understands intuitively what flower expressions do? Okay, so great. Now I'm going to tell you more formally how to understand them. Most of the time, you don't need that formality because it's just intuitive, but in case it becomes more complex, I want you to understand. The next thing I would like to tell you is that in SQL, the order of the clauses is fixed. It has to be select, from, where, group by, having, order by, limit, offset. Who knows that by heart? Should know that by heart, right? But it's fixed. In SQL, it has to be in that order, and you cannot change the order. Well, in JSONic, you have full freedom on the order in which you want to put your clauses. There's just two conditions. The first clause has to be either a for or a let. The last clause has to be a return. Apart from that, you can put the clauses in any order you want. So you could have a let, for, let, where, let, for, group by, let, order by, let, where, order by, let, group by, for, order by, let, group by, where, return. And that's fine. That's a flower expression. Okay, that's super convenient. And again, that was designed by the same people who invented SQL. So they really were aware of the limitation of the select from where in SQL. And they just came up with this generalized select from where that can have any number of clauses in any order, right? Just for, let first, and return at the end. That's the only constraint. How does it work? Well, I have a visual for you. What happens is that you can actually visualize it with data frames. In fact, it is implemented internally with data frames. When you have this $4 you basically want to bind one by one. Imagine that each row in your data frame that is hidden somewhere corresponds to one binding, and you call the column with the name of the variable. So X is bound in turn to the integers from 1 to 10. Then what happens is that the where clause is going to filter by executing the predicate on every one of the bindings, every one of the rows, getting false or true. And what happens is that you only keep those for which the where evaluation is true, 8, 9, 10, and you return that. Now you have a new list of bindings of X to just 8, 9, and 10. Who is with me? Right? And then when you compute the return, for every row in your data frame, you compute that, and that gives you the output as a sequence of 3 integers. This is called the tuple stream semantics. It means that every clause technically returns a tuple stream. A clause is not an expression. An expression always returns a sequence of items, but a clause is not an expression, right? So this is why it doesn't return a sequence of items, it returns a tuple stream. And think of the tuple stream as a data frame in this way with the visuals there. This is only a visual because as the user of JSONic, you don't need to care about that. This is just for defining the formal semantics and for the physical implementation. Here, for example, I have a for from 1 to 5, then a let is going to create a second column in my data frame, and then I return the product. This is what it returns. Who agrees? Right? So I go top down, clause by clause, and I evaluate a data frame, a data frame, a data frame. RumbleDB, the engine, actually builds these data frames. It means that it happens on Spark as Spark data frames, and it even works with billions or trillions of bindings in exactly the same way, just because it executes with data frames on a cluster. Okay, what about the group by? Well, let's look at it. $X4 is going to create this. The group by, so we evaluate the key every time. Now you see everything that has a 1 will be together, and everything that has a 0 will be together. So the first, third, and fifth row are together, and the second and fourth row are together. And then you do it like this. So Y is the key. So here it has the unique value. And X, now you grouped them together. So now 1, 3, and 5 are together. It's a sequence of 1, 3, 5, and then the sequence of 2, 4. You basically put the even numbers on one side and the odd numbers on the other side. Who is with me? right? And then if you evaluate now using these bindings, the object, it's a dynamic object, then you create foo1 with bar3 if you take the count of the sequence. So 135 has a count of 3, 24 has a count of 2, it returns this. Who agrees this is what is returned? Okay, for whom is that intuitive? Right, great. So that's the group by and so on. So now if I come back to my examples, here, what do? I iterate on the events. For every event, I look at the number of commits, which is the size of my array located at payload commits. Then I order by commits descending. So it means that I put first those with a huge number of commits and then less and less and less and less. And then at the bottom, I have those that might have 1 or even 0 commits, an empty array. And then I project. Projecting means that I don't heap all the keys. If I would just return $events, that would be the whole object. Project says I only want the keys ID and type, right? It doesn't look like in SQL, where in SQL you would put the names, a list of names, but that has to do with the fact that it's more flexible than SQL. So you might want to project on the keys dynamically and not as part of the query like in SQL. It's again for flexibility. So this is why we have a project function, okay? All right, so now you have a list of events by decreasing number of commits. What do I have here? Now I want to group, I want to build a histogram. What if I want to build a histogram of my events nicely bucketed by number of commits? Who knows what a histogram is? Okay, awesome. So I just group by the number of commits, right? Look at the size. Why do I have this 0, 1? That is a trick. That is a trick. Let me explain why this comma 0 and that 1. The idea is that size even payload commits, it's flexible. It's a collection of trees. So it means that commits might be absent. You might have some of the objects that don't have any payload commits. If that's the case, that's not going to throw an error. It's just going to return the empty sequence. So that's going to be empty. Size is going to be empty. What do we do when it's empty? I don't want to have something empty in my histograms. If it's empty, I want it to be 0, right? And there is a small trick. It's a bit geeky, but what people do is that if they want to say, if it's empty, that's 0, they just append the 0. So now you have a sequence, the concatenation of that, and then you take the first. What happens? Well, if it's not empty, this is the first one. So if it's not empty, it's taking this. If that is empty, then the first one would be the 0, because then there would be nothing in there. So this is just a trick to fall back to a value in case it's empty that looks like this. Who understands it? Right? That's also something that in SQL would be more demanding. You could do it in SQL, but it makes it easy. So you see, even if the data is not clean, you have a way to clean it up. Then you order by number of commits. Now you see it's nicely organized. And then you have commits is the number of commits is the count. That's the count of my $events here, right? And then you can copy paste that, save it as CSV or download it and put it in Excel or FreeOffice or LibreOffice or whatever and get a nice plot, or use Python matplotlib, for example, okay? So this is the sort of things you can do using JSONiq. In fact, with JSONiq, you can support the whole relational algebra. And I'm going to show you with a concrete example. It shouldn't surprise you, right? Because these flower expressions look a lot like the select from where. So after all, there's no reason why we couldn't do the same: projection, selection, and so on. So I'm taking 2 collections. Imagine a collection of products that have very simple objects that look like this with just 3 columns. And on the right, a collection of stores. Who agrees that in that case, we actually have 2 relational tables? Who sees that? On the left, we have a relational table with how many columns? 3, right? ID, type, and store. And on the right, with how many columns? No, I know you know, right? Who thinks 2? Okay, I know you know. So ID and country. Okay, so let's call it products.json and stores.json. Now we could do it in SQL, obviously, if we consider them as tables, but I want to show you in JSONiq. So first, how do we do selection? Well, you know that selection in SQL is done with the where clause, right? So in JSONiq, it's also the where clause. So if you want to select some of the objects in your collection that fulfill a certain predicate, that satisfy a predicate, just use the where clause, and that's it. How about the projection? When the projection is this project function. So you just iterate over your collection, and for every record of the collection, every object, you project to the columns you want, ID and type, right? By the way, that's a way to clean up. Imagine that you have a lot of extra columns that you don't care about and that are very messy. Just project to those you want, and now you get something that just has these two columns, right? ID and type. It might be heterogeneous though, because it might be that ID is sometimes an integer, sometimes a string, so it doesn't protect you against that, right? But at least you know that you're just going to have these two keys, ID and type. Ordering is order by, right? So you can reorganize the collection sorting by IDs, right? And group by, aggregation, is using the group by. Now it's done like SQL because I'm using an aggregation on the variables that are not keys, right? So key is aggregated to counts. But again, remember that in JSONic, you don't have to aggregate. It would also be fine not to aggregate. Then you just create nested structures in the outputs. Okay, who is with me? Selection, projection, ordering, sorting, aggregation, joins. How do we do joins? Well, just with two fors. Remember how you do a join in SQL? Select from table 1, comma, table 2, where the joining criterion, and then that's it, right? So that's how you do a join. It's very similar here, for, and where. So you iterate on the products and on the stores. Now, if you stop here, you would have all combinations. That doesn't make sense. You only want the combinations where the store matches the product, right? So you match the ID of the store from the store with the actual store value in the product. And that is what you get. Now you return the type and the country. Now you see that that data set is a combination of the original data set, right? Because the type came from the products collection and the name of the country came from the stores collection. Who sees that? Who sees that it's a join? Okay. Now I have good news for you. You can try that with billions of objects on both sides and it will work. The reason is that RumbleDB auto-detects that there is a join and it will implement it as a join on top of Spark. And Spark is also good at computing a join. It's a bit less efficient than projection or selection, but it works. Now, left outer join is just a special kind of join in the case that not everything has a match. For example, imagine that a product doesn't have any store. You have an object in the products collection that doesn't correspond to any store. You can catch that with the allowing empty. You can just say for $S allowing empty in, and then you have JSON file stored and you filter the stores that match the ID, right? Instead of a where clause, you put it in a filter there. This allowing empty is going to say, well, if there is no match, that's fine. Just bind it to the empty sequence, right? So what's going on is that if you have, for a specific value of P, no store in there, that's the empty sequence. And because of the allowing empty, the $S is going to be bound once to the empty sequence. What happens is that then this is the empty sequence, and the empty sequence is automatically converted to a null when you execute it. If you didn't have the allowing empty, that would just disappear, right? Because then that would be empty and there would be no binding at all. So without allowing empty, with allowing empty. Who is with me? Okay, that's called the left outer join. Now, what about denormalization? It's kind of a more elaborate kind of join that SQL can normally not do. What if we want to join the countries and the stores, but what I want to do is nest the products inside the countries. I basically want to output a collection of all countries, Switzerland, Germany, United States, and in every country, I want to list the products that are sold in the stores. How do I do it? Again, something that looks like a join, but I use a let clause. So I iterate over the stores, right? Then for every store, I list the products. So what I do is that I filter through the collection of products. I filter on the store. So I only keep the products for the current store that I'm looking at. And I put it in $P. So every binding will have $S, which is a store, and $P, that is the sequence of products in the store. And then I return, imagine there's one store in every country, just to keep it simple. Then I output the country of the store. And inside a nested array of strings, I list the $P.type, right? That's again the beauty of having a language that is more powerful than SQL and that supports denormalized data, that supports nestedness, right? Who agrees with that query? Okay, you can try it out. Again, everything you can play in Jupyter Notebooks, play with it. It's normally, it should be very intuitive. What does the $$ do? Well, that's for your predicate. Whenever you have a filtering predicates like this in the $$.store, here, the $$ is basically be one by one bound to the items that come from here. That can be a billion items. For every one of these items, you need to evaluate this here, and the $$ is the current item. It's called the context item. So the first time, this will be the first product. The second time, it will be the second product. The third time, it's going to be the third product. And you evaluate that a billion times, as many as product. Every time, this is the current item coming from here, right? Always one, right? It's $$. If you want to draw a parallel with Spark, do you remember when you use the filter function in Python, in PySpark, with the lambda filter, lambda x, a row something, f of x? Well, it's to avoid having to define a lambda. Instead of lambda x and then something that depends on x, just go ahead with the $$, right? And you don't need to explicitly define the lambda. For whom does that make sense? Okay. Good. All right, but it's good that you ask, right? Because this $$ can be confusing at first, right? You can only use the $$ when you have a filtering predicates like that. If you use the $$ somewhere else, that's going to be an error, right? It has to be in a filtering predicate. Okay, what about types? Do you remember the whole type system that I introduced you in the data modeling? When you have them all here, you can check for the types. So you can do let $path as string, let $events as object star. Remember the occurrence indicators? Star means 0, 1, or more. Plus means 1 or more. Question marks means 0 or 1. So you can use the types in this way. What it does technically is just that it does these additional checks. It executes your query, but on top of that, it also checks the types. If one of the types doesn't match, it throws an error at you. So it's a good idea if you want to be extra safe when you execute your query, you might have done a mistake in there, add the types in there, and that's a safeguard. Then it will warn you or throw an error if any of the types is not what you expect, right? All you need to do is add this as followed by the type in the let variable, right? Now, this is how they look like. Integer is a sequence of exactly one integer item. Boolean is a sequence of 0 or 1 Boolean items, so either the empty sequence or a single Boolean item. Array plus means a non-empty sequence of arrays, can be 1, 2, or more arrays, that's the plus. And the star means a sequence of objects, possibly empty, right? The difference between plus and star is that star allows for empty, plus does not allow for empty. Who already heard of regular expressions? So if you know about regular expressions, that shouldn't surprise you, right? The question mark, the plus, and the star have exactly the same intuition. So you can put them, for example, that's let $x, that's a sequence of 2 arrays, so it matches array plus, that's fine. You can also have plenty of more expressions like instance of integer star will return true. It's testing whether or not an expression returns a certain type, right? So that's going to return true or false here. Who thinks it returns true? Who think it returns false? It's false, right? Because it's not everything is an integer. The second one is a string. So that will fail the type test. It would have to all be integers. Too much. Then you have castable. Castable just tests. It tells you whether it would work or not. Could you cast 3.14 as a double? Yes, you could, so that returns true. If you try foo castable as double, that would return false. You cannot cast foo to a double. Okay. Then you have functions. I didn't show you the functions yet, but you can actually also write functions. Declare functions, and then you can add types to the variables, to the parameters of your function, and you can have also a type for the return value of the function. Right. Is there a question on Zoom? Could you cast a string?
Could you cast a string containing only digits?
Yes, absolutely. If you put a string with digits with the double quotes and the digits castable as double, it's going to return true. Yeah. And then you could do cast as in order to actually cast it, right? Does it make sense? Yeah. Okay. So That's a function with types. The types are optional. If you don't want to put the types in the function, that's fine too. All the part that is in red, just skip it and remove it, and that works as well. You just don't specify any types. By default, the most generic type is item star. Item star means a sequence of items. So if you don't know, it's item star implicitly. Okay? Now, we can validate data. Imagine you have some very messy data set, you clean it up. So the code inside we've seen before, these 4 events grouped by, that's the histogram. Remember the histogram we've done before? So we built the histogram. What if now I would like to validate it because I want to put it in Parquet or CSV or whatever? Well, what I need to do is define my schema. How do I define my schema? With a type declaration. So all I need to do at the beginning is declare type local histogram. Commits is a short and count is a long. I actually had fun here. I could have just put commits integer and count integer, right? But just wanted to make the point that you can put any types in there. So commits is an integer and count is an integer. And then you have this validate type. And then it's going to actually check that it's valid against this schema. What do you get when you validate a collection of JSON objects against a schema? Providing that the schema fulfills some constraints, you get a df. What do you get? A data frame, exactly. So when you do that, you will automatically get a data frame. It's just hidden from you. Physically, you will have a data frame. And it means that you can save that as Parquet, as CSV, as Avro, as basically a binary format with a schema, right? So a very common thing to do when you download a data set from the internet in the JSON format, and after cleaning it up, create a schema, validate it, looks just like this, validate it and save it as Parquet. Then you query the data reading from the Parquet file. It's going to be much faster than reading it from JSON. That's one of the few tricks that data scientists can use to accelerate the queries. Okay? All right. So here's an example. I have the query with that I call query.jq. That's my query. Then I have, so of course you use Jupyter notebooks, right? So you don't need to do it. But actually, if you wanted to save it somewhere, you could use a Java jar command. There is just a single jar file for RumbleDB that you can download. Then you execute it with Java. And then you say where you want to output it. So I just called it out, but it can be any path on HDFS, S3, or your local file system. Overwrite yes, because in case it already exists, I want to erase it. Number of output partitions is just to make sure that there's only one shard, that it's all output to a single file instead of many. Output format CSV is going to create a CSV file. And header true, it's to make sure that it adds the commits and short headers in the CSV file. And after I've executed that and I double click on it, it magically appears in Excel or Numbers or LibreOffice or whatever you want. So this is the whole chain where I executed my JSON query, validated the output, saved it as CSV, and then I can open it, sorry, in a spreadsheet software, okay? Okay. Now, who is with me? Okay, so that's the practical aspect. That's how to use it. You will have this at the exam. Not this, of course, but writing the query in Jupyter Notebook, you will have that. And in the exam, you will have questions where we ask you how many of these are there, what is the most popular singer, and that kind of questions, right? Okay. Now, I want to say a few words about the implementation. How is it actually implemented? And that was done by your predecessors, by master students, bachelor students. 20 different students actually contributed to the engine. Many of them actually took the big data or the big data for engineers class. So what happens behind the scene? And in fact, a lot of that is also true for SQL and for relational databases or even for languages in general. So it's pretty standard. When you type your query in the Jupyter notebooks, it's just text. The first thing that an engine will do is parse it. There is some grammar rules, and then it's going to build a tree. It's called the abstract syntax tree. Who already heard of that? It's just an in-memory representation of your query, right? So the query, as understood by the computer, is on the right. It's just a representation of the same, right? Of the syntax. The second thing that happens is that there is a bit of post-processing, and then you create an expression tree. An expression tree is basically when the computer recognizes your Lego pieces. right? So each expression is a node in there. So you can see you have a count, and inside the count, there's a flower that has a for clause and a return clause, and so on and so on. So this is all hidden from you, but this is what happens. So the Lego assembly is the expression tree. Then the engine is going to optimize. It's going to figure out a few inefficiencies because maybe you as a user didn't write your query in the most efficient way, but that's not a problem because the engine is smart enough to do a few fixes. For example, it might notice that you put a variable in a let, but you're not actually using it. So at that point, the engine can just remove it. It's like this variable is not used, let me just remove it. That's a concrete thing that the engine can do. So it means that putting unused variables in your query is not going to make it slower because it's automatically removed anyway at that point. That's called the optimization. Then we generate an iterator tree. An iterator tree is kind of the compiled code that you output from the query, and that is executable. And the iterator tree is what we are going to use when we evaluate the query. And the way an iterator tree works is that this is the machinery of your query. You basically pull a string here, you just pull here, and the items come out one by one. Or they could come out as an RDD or a data frame and so on, but you just pull a string here, and when you pull the string there, it's automatically pulling all the strings recursively in the sequence. So you pull here and it just lifts all the items up. So an iterator tree is called iterator because it spits items one by one. Who is with me? Okay, that's very physical. That's already advanced, right? This is the sort of things that normally we teach in computer science master's degrees. Now, just so you understand what's going on, imagine I have a simple iterator, just a for return. You know that it's a clause, right? The for is a clause, so it's going to output streams of tuples. So imagine that I have this collection, these tuples here, field 1, 6, 4, 3, 2. First, I'm going to describe to you what is a materialized execution. A materialized execution means that when you have the for iterator, we are going to pull all the items out of it, all of them. I just block here, I take all the items, tack, 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 all of them, right? That's called the materialization because I actually have them in memory in that order. Then I compute with my return iterator, maybe I extract the integers and so on, right? So this is called the materialized execution. Now you probably see the limits of that because imagine that you have 1 trillion such items, right, on your hard drive. Imagine you have 1 trillion items. If you try to materialize and really produce them one by one and keep them, at some point your memory is going to overflow because you cannot fit 1 trillion items in a laptop. That doesn't work. Who agrees? Right? So you cannot materialize a sequence of 1 trillion items on your laptop. So what do you do in that case? You do it like Netflix, you stream. So it means you take the first item, you process it, you spit out the 1. You take the second item, process it, spit out the 6. Take the third item, process it, spit out the 4. Take, tack, tack, tack. Who sees that I can do that 1 trillion times? And I will not exhaust my memory because I throw it away every time, right? This is called streaming, just like the same streaming as in video on demand, right? When you watch a movie on Netflix, it's downloading a few seconds of the movie or of the series, a few seconds, then you watch it, then it throws it away. So this is why you could technically stream 10 hours of movie. Materializing would mean that you download the entire movie to your laptop, right? You download the movie. Streaming means you only have a few seconds at a time and you throw away as soon as you've seen it. Who understands the difference? Right. So again, downloading a movie and watch it offline as opposed to streaming is the same difference as between materializing here and streaming, right? But it can take a lot of time because 1 trillion items, you might still be here. The age of the universe might not be enough, right? There's only so many years since the beginning of the universe. So it can take a lot of time. What do we do when things would take a lot of time on a single machine? I want to hear it, I know you know. What do we do when it takes too much time on one machine? We parallelize, exactly. So if we parallelize, we just use more machines and we spread it over. and then we execute. Note that we could also stream in parallel. That works together, right? We could also stream on each machine, or we could materialize on each machine, right? So that's the idea. So you see how you have so many ways of executing the same thing. You can materialize, you can stream, you can parallelize. It doesn't always all work. Sometimes you have something that works, something that doesn't, but in general, you have a choice. And of course, that would consume a lot of machines, but again, there is no free lunch, right? So that's it. I will just finish next week. I probably have a few slides to finish, but I really want to again insist that this thing works on S3, on HDFS, from HTTP. You can download from the web. Just be aware, if you use HTTP, that will not parallelize. You cannot parallelize from the web. The web is not parallel, but you can parallelize for S3, HDFS, and so on, locally, Azure, Google Cloud, all of these formats. Now you know that Parquet is going to be faster, JSON is going to be slower, and so on and so on. So let's stop here for today. And I have a few more slides that I will just, maybe 20, 30 more slides that I'll finish next week. Next week, I'll just wrap up everything. We'll have a big quiz game, so please come. It's even more fun if those who usually come on Zoom, then come to the lecture hall next week, maybe. We'll just celebrate together and play the quiz game, right? And spread the word to your colleagues, even those who usually watch the recordings. Do come. We are going to rehearse for the exam and go through the material. Okay. So thank you very much. Everybody enjoy the exercises that the TA team has prepared, and see you next week for the celebration of the end of the semester. Thank you.